session 3 of, actually I don't know, how many people say tidy versus tide?
Tidy.
Tidy.
Is it tidy? Okay, welcome to session 3 of tidy. We have Liam here to speak about applications of applicative proof search.
Thank you, Richard. All right, so today I'm going to talk about proof search problems. So there's been a few high-profile examples from the field of mathematics. For example, we have the Kepler conjecture, which says that that is the optimal way to pack a bunch of cannonballs. We also have the four-color theorem, which says that you can color any map. Here is the prefectural map of Japan, using just 4 colors, and you won't have any neighboring regions that use the same color. So these proofs have been completed, but they were completed with the help of computers because, well, they used a lot of complicated mathematics. They were able to boil it down to only about thousands of cases. Thousands is a lot, but it's still finite. So you can have a computer that runs through every single case and tries to exhaustively analyze every single one to determine whether or not the theorem is true. So these proof search programs caused quite a bit of controversy when they were first introduced because, well, you've got this program, P, and it corresponds to some proposition, for example, the Kepler conjecture or the four-color theorem, and it's going to evaluate, it's going to return a value like true. Right, so I evaluated the whole program, and it came back with a result, yes. Does that really mean what we think it means? Does it really mean that the proposition that you're relating to the program is true? So there was a whole bunch of effort later on to verify these proof search programs. So for Coq, there was the four-color theorem was verified in Coq using a whole lot of machinery, and there's a similar set of machinery in Hall 4 for verifying the proof of the Kepler conjecture called Fleispec. And they just established that if the program evaluates to true, then the proposition that the program is related to holds. So it's all this work to relate a program and a proposition. But we already have something that relates programs and propositions, and that's a type system. So my idea is to create a type for proof search programs rich enough to encode the proposition that the proof search program is attempting to actually prove. So we're going to make the type checker work very hard here, hence the graphic. So we've got this one little bit inside of, this is a standard dependently typed typing rules, but we've got this little bit of evaluation in here. So we can use this evaluation to do arbitrary computation. For example, we can run through an entire proof search and try and come up with a proof for a given proposition. So I've developed this library of typed proof search procedures, and they're compositional. They've got this really nice API that uses applicative functors, and I'll talk about that in a minute. So why do I want to do this? Well, if we can type proof search procedures with the proposition that they attempt to prove, then we'll know that they're correct because we'll be able to include a correctness proof inside the type of these procedures. We can integrate, because it's embedded in a dependently typed language, we can integrate the machinery of manual proof with automatic proof. We can compose them together using nice interfaces. We can push Agda's type checker to the very limit of its capabilities and see how far it goes before it breaks. And it's kind of fun to do this. So this is my motivation anyway. So this is the type that I've defined for proof search procedures. We call it a Hemi Decider in the paper. I'll talk about that in a minute. But basically it just contains a field found, which is a Boolean, yes or no, whether or not I found the proof. So this is the standard result from the ordinary proof search procedure. And then we have the verification of that result that says that if the Boolean is true, that T thing is just a inhabited if and only if the Boolean argument is true. If the Boolean is true, then the proposition P holds. So this is the soundness proof for the decision procedure. So it's called a Hemi Decider because it's not really a semi-decider, but it's still half of a decider. It's difficult to name things in computer science, but I'll leave it there. Okay, so we can compose these things together. We can use the functor instance to combine manual reasoning with proof search. So I use this nice little diamond because you can, if you look at these decision procedures through a Curry-Howard lens, you can sort of view it as a possibility modal logic. So you could sort of say that a proof search procedure for A is possibly A. Maybe A is true, right? So if A implies B and maybe A is true, then maybe B is true. Applicative, we can use applicative to conjunctively compose things together. So this is the standard interface for applicative, the app operator, but a nicer way to look at it would be if you've got a proof search procedure for A and a proof search procedure for B, you can combine them to get a proof search procedure for A and B that succeeds only when both of the proof search procedures succeed. Right? And alternative, so we can compose two together and succeed if either one of them succeeds similarly. So we have both applicative and alternative. It's a very nice little interface. It's also a monad. So we have this bind signature here. If I have a proof search procedure for A, and then I have a proof search procedure for B that's dependent on the proof object from A, then I can chain them together to get a proof search procedure for B. But this is not the most useful function because in order to construct the proof object, in order to run the second proof procedure, we need to actually apply that function proof, which means that we actually need to construct the proof object. With the applicative and alternative instances, we can get away with just doing computation on the Boolean and then constructing the function separately, so that if you don't need the proof object, you just want to know whether or not it's inhabited, you don't need to do any examination of the proof object. But if you have this monadic interface, suddenly you have to make these proof objects all the time. It can get very expensive. So for efficiency reasons, you actually want to use applicative functors more than monad. Now, in my experience, I've never found a use for this monad function, trying to automate various proofs, but maybe there are some examples where it's needed, but I haven't seen any. So we can reflect these proof search procedures by saying we've got a function here that takes a proof search procedure. If it succeeds, then the type that this function returns is P, the proposition, and if not, then it's a trivially inhabited type. And then we can extract the evidence. So we can use these proof search procedures as a tactic to construct proof objects for us wherever we might need them. So I'll show you some examples, but first I want to talk about some of the applications of these proof search procedures. So the first application I looked at was trying to encode a property-based testing library in Agda. So a property-based test is actually just a proof search. What you're doing is you're searching for a counterexample to a given proposition. So you're just searching for a proof of the negation of whatever property you want to hold for your program. And it's also, you've also got some other bits and pieces. You've got some source of input data. And so we model this. A property is just a decision procedure, or rather a Hemi Decider, parameterized by a depth, a search depth. And we provide a combinator that takes a stream, a co-recursive stream of inputs, and a property dependent on that input, and we'll search through every one of those inputs up to the given depth. So depending on the type of stream you use, you get two different types of testing. If you had a random stream of elements, it would be more like quick check, where you're picking elements randomly. And if you had an exhaustive enumeration technique, then it's more like small check, where you start at 0 and then 1 and then 2, and so you build up, and eventually you'll probably traverse every single element. We don't verify that fact, but yeah. So there's a paper where they implement quick check for Isabel, and it turns out they did some empirical analysis of which method is better for a proving things approach, and they found that exhaustive analysis was better. So that suits us because encoding a random number generator in Agda's numerics doesn't sound very fun. I'm sure some people might have tried it, but I gave it a go and I couldn't get it working. So we started with the exhaustive enumeration, and so if you want to create an exhaustive enumerator of a sum type, then you have the two input streams and you just fairly merge them together. And if you have a product type, then you can just diagonally traverse the plane, as in that diagram here. So you can build up all of the streams for all of the usual types using these methods. So some examples. I can write a program that says that find me a Pythagorean triad, and or another example, if you have I squared plus 7 and I plus 1 squared plus 7, a lot of the, if you try this on low numbers, it always seems to be co-prime. But this is actually not true. So we'll search for a counterexample using this library. So Agda might do a little bit of work here, but eventually you can reflect this into the type level, and then you end up having a lemma. Exists an I such that I squared plus 7 or I plus 1 squared plus 7 does not have a GCD of 1, i.e. they're not co-prime, and that I, if you actually look at the value of lemma, will be 14. Okay. I tried it on some more complicated formulas that have this property up to higher numbers, but then Agda wouldn't finish. It would run out of memory. Okay, but I'm not done with just property-based testing. I want to do a model checker. That sounds like a much harder proof search problem to encode, so let's try that. So a model checker is essentially solving a simply stated but hard to solve problem. And the problem is, I've got a model of a program. In this case, it's going to be some sort of computation tree. So a tree where you've got an initial state at the root, and then every child is a possible descendant of that initial state. And it can go on infinitely in certain directions. So we have this little thunking operator here for co-recursion. And a formula is just a property of a tree parameterized by a certain observation depth. So you only look at a certain prefix of the tree. Okay. So a model checking procedure then is, for a particular formula phi, is just a Hemi decider parameterized by a tree and a depth. So because we're only observing a finite prefix of the tree, then I only really want to care about formulas that will remain true if I increase the search depth. So if I find that a formula holds for a certain depth, then it should never become false if I increase that depth. Okay? So we just make sure that we encode the satisfaction relation by saying that there exists a point d0 after which the formula holds for every depth. Okay? So the logic we use for formulas is a very small subset of CTL, so the computation tree logic. So some examples of operators in this logic are E and A are the path operators, and then U is the temporal operator. So the path operators say that there exists a path, for example, for E, where the blue holds until the red holds. And you can see that, I can't really demonstrate, I can just run over. You can see this path here is the path where that first formula holds. And then the second one is for all paths. You can see the first node is blue, and then the second node, regardless of which path you take, is green, has a little hollow green circle, so therefore the second formula holds as well for that tree. Because A is for all paths and E is for one path. So we can encode these formulas as data types in Agda, just as normal, and we can even write proof search procedures for them, just using the standard applicative and alternative instances that we defined earlier. And the full implementation of all of this is in the paper. And we can define derived operators like the finally operator, which just says that something must happen at a certain point in the path. But when we try and define global operators that say for all points in a path, something must be true, we can't do that because we're only observing a finite prefix of the tree. So therefore we have to say, we'll only look at the terminating cases. So we add an extra thing completed here, which says that it's only true when the state has no descendants. So then, if AG phi, for example, is that for all paths at all time, phi is true. So we just say for all paths, phi is true until completed and phi is still true, right? So this is a restriction of the logic, a severe restriction, but it still works for our use case. So specifying a model as a computation tree directly is extremely painful. So let's use Automata instead. So we've got a diagram here, which is just it's got a label set and a shared state set sigma, and a transition function that can have many possible, so it's non-deterministic, and it's got an initial state label. And we can compose these things together in a parallel composition. And these parallel compositions can interfere with each other because they have the same common shared state sigma. Okay, but automata aren't very friendly to write either. I mean, they're a bit better than co-recursive state trees, but they're not that great. So let's write an embedded language. I've embedded Dijkstra's guarded command language inside Agda. And then by way of structural operational semantics, the full details are all in the paper, you can get the diagram for a given program. So now with all of that machinery done, we can actually verify some programs. So here is Peterson's algorithm for the critical section solution, which is a concurrency problem where you say, I've got two programs and they both want to run some bit of code called a critical section, CS1 and CS2 in these examples. And we want to say that these two processes, they're running simultaneously, should not be running their critical sections at the same time. This is called mutual exclusion. And so we can define that in our logic, and we can define a proof search procedure for it just like that. It's very simple. And similarly, we have another desirable property, starvation freedom, which says that both processes will eventually get a chance to get into their critical section. And we also do termination, but it won't fit on this slide. But it's much the same sort of thing. So now we can take the semantics of the two Peterson's processes, compose them in a parallel composition, get their computation tree, and then we can write a property that just searches for a depth such that it can satisfy all three of those desirable properties for a concurrency solution. And, well, you wait a long time. It takes about actually, with the latest version of Agda, it's not too bad. It's only about 5 minutes, I think, maybe a bit less. Then Agda will finally give you a proof that the program, satisfies the properties of mutual exclusion, starvation freedom, and termination, which is lovely. So I didn't actually have to write any proofs here. I didn't have to discharge any proof obligations. I just needed to assemble all of the necessary pieces. So there's a lot more in the paper. There's Decker's algorithm. We also do Decker's algorithm. And in there we encounter some problems with verification, so we can only really do sanity checking. We have the full semantics of the GCL embedding and lots of other stuff. The library is available online at that address. And there's a whole lot of future stuff I can do here. A lot of this stuff is very basic. The model checker is very basic. I'd like to do some LTL model checking or something like that using Buchi automata. I'd like to look at using Agda's reflection mechanism to automatically figure out a property or a proof search procedure for a given goal. And improving performance of both my proof search library and Agda's evaluator itself would be useful to make more powerful properties encodable in this system. Thanks.
James McKenna will be the discussant for this paper.
The speaker and his talk speak for themselves. I can only encourage you to read this paper. It's one of the most fun, fabulous pieces of engineering that I've read in a long time, which covers more ground than is reasonable in a PhD student. I could stop there, and perhaps for the sake of his blushes I should. Let me ask you a question about it, though.
Yeah.
You've done all this work, which is very impressive in exploring finite parts of potentially infinite state spaces, already mobilizing stuff that allows you to explore infinite state spaces to the bitter end via co-recursion. Why can't you get those extra LTL and CTL operators working
I'm pretty sure I could, but...
Well, why didn't you do it in the paper then? Because you'd already done so much that just seemed within reach.
Yes, so... No, so I do think that you're right.
Okay,
I do
good.
think we can get there. The thing is, all of the examples here have a very direct correspondence, connection between what the proof search procedure is doing and what the proposition that they're actually trying to prove is encoding. Okay. Whereas if you tried to do LTL model checking or something like that, then there's a bit more distance there to cover.
Because you would end up having to express kind of infinite unfoldings of the proposition as well as... Right, okay.
Yes.
Okay, so it's good to know there is a hard thing left to do. Agda fans will also think this is a very impressive advert for Agda as an engineering tool for meta theory. And indeed, I think that's an important take-home. But I wondered if you were being a bit, what's the word? You were going for the low-hanging fruit of the type system rather than really exploiting type dependency in a meaningful way. So in particular, by focusing on the applicative interface, you say, here's an engineering trade-off. I don't want to examine certain arguments in the type, so I'll encapsulate it in my diamond abstraction. What happens if you take type dependency in Agda a bit more seriously in terms of how even that Boolean is carried around? So when you conjunctively compose things, you know that that Boolean is indeed the sequential AND of the Booleans of the two arguments. When you do alternatives, you know it's,
right.
I guess, the sequential OR of, is it, or is it the parallel OR?
No, it should be sequential.
Okay, okay. Is there anything we can get out of knowing that? Or is that just a runtime artifact that we don't care about?
That's something I haven't explored in detail, so that would be interesting to look at.
And then a final point, I want to say that the first two examples you had, strictly speaking, are not proof search problems that machines introduced. They're proof search problems where the search space was defined by humans, and then simply the checking of the cases was done by machines. There was no actual exploration of the state spaces. Here, you've actually done more. You've given machinery to explore those state spaces as well. So a minus one for gentle inaccuracy and a plus n for providing something better. So thank you very much. Questions, please.
Yes?
So most model checkers work by, they have some kind of X state thing, and the state is represented as some kind of Boolean formula, and they have some kind of normal form of Boolean formulas, so like a BDD or something. You keep pushing the next state, you reach a fixed point, and then you know that, well, all other states are equivalent. Can you use a strategy like that?
So I think yes, but there's a lot of caveats. So I tried to do, I haven't tried with BDDs, but I did try and do the basic LTL model checking algorithm where you build up you annotate the formulas on each of the states until you've got the formula you want. And the problem with this was just that I didn't know how to represent it such that I could keep the connection between, how can I say this? So in the model checking algorithm, you usually treat the formula in a very syntactic way. You just sort of break it down into its components and you can assemble it all up again. And in my library, it's all very opaque. The proposition is just P, right? So you can't really just break it down like that. We need to have some sort of syntactic access to the formula and stuff like that. And then keeping the correspondence between the syntactic formula and the semantic formula is rather difficult. So there's work to do there, yeah. Yeah?
So your diamond type at the start looks logically equivalent to just a maybe type.
It is.
So the only reason for that you do this way for efficiency?
Yes. So originally it was a maybe type. And I posted an email, some of you may have seen it, to the Agda mailing list. And Ulf Norrell kindly told me, oh, you're doing it all wrong. Just do this and it will be way faster. And I tried it and it worked. And so I rewrote the whole library to encode that technique, yes. So I should have mentioned him in this thank you page, by the way. Yes?
So the trick you do to get it to be quick is to separate the computation of the proof from the kind of
the presence of the proof, yeah.
And the Boolean, which which is easy.
So we manually, we delay the construction of the actual proof until you actually need it, because quite often you'll end up with a situation where, say, you're doing one proof first, and then you do the next proof, and then that fails. So your overall proof has failed.
Right.
So what's the point in constructing the original proof object? So instead, you would just make it so you can get access to those Booleans and efficiently compute whether or not the proof exists, and then if you really need it at the end, then you can get the proof object out and actually construct it,
So why is it still slow?
It's still slow because, okay, so there's a few reasons. So for the GCD example, it's just because apparently, I haven't looked at it in detail, but the GCD implementation in Agda standard library is really slow. There are ways to make it better. Ulf told me, I haven't looked at it. But for the model checking example, I think it's actually quite fast, considering the naivety of the model checking algorithm that I'm doing. So it's just exhaustively analyzing the entire tree, so that's going to take a while regardless of what language you put it in. Yeah. Yeah?
I had a PhD student in current so he did some work on model checking, etc. in Acta. Based on the idea of that you use an external tool for doing
Right.
the proof search, and then
Replay it
in
in.
order to construct a proof object. What we did is we implemented a naive procedure and overrode it by the thing, and this way you get an explicit proof object. That was somehow the trick.
Right.
So,
Sounds interesting.
So you actually don't run this proof search. So the inefficient procedure is usually not executed unless you actually want a proof object.
Right.
When you don't have a proof object, then this inefficient thing works.
Right. That's interesting.
And it did, so of course we didn't do any. We did only. It works only for decidable problems. Because if you have a semi-decidable problem, then you don't, because then you would need the guarantees that the system which overrides gives you exactly then an answer, then your correct implementation does it, and that becomes
Right. Yeah. No, that's very interesting. Do you have anything I could look at about that, or?
current console.
Okay.
KANSO.
Okay, I'll look it up.
PhD,
Great. Thanks. That'd be very interesting. Anyone else?
And I'm keen on that somebody takes it over because it's an impressive implementation in Acta, which has not been maintained since. So. And it's some gold to be picked out.
Anyone else? Okay. Thank you very much.